Okay, so good evening, everyone. Um, Today, welcome to another lecture on machine learning. Today, we will be talking about linear regression and one of the most important concepts of machine learning, which is bias variance trade-off. It is not very easy, to be honest, at the first try. These lectures will be very mathematical, bit theoretical as well. I expect some beginner knowledge on probability. In essence, what is the expectation of a random variable? Let's say a random variable x is given. What is the expectation? It's very simple. Just integral over all data points um, x into probability of x dx. I hope you know these things, because if you don't, then this lecture will be a bit difficult to understand. So I would suggest you guys to go back and first learn about that concepts, and then try to follow the lecture along. Then it will be very easy. But still, I will try to make sure it is as simple as possible given this format. So let's begin. But before I begin, as always, we will be discussing a few questions on the computer science part, which is common across data science and computer science. The question we'll discuss, I'll focus my discussion on algorithms because that is the most important subject for both the subjects, for both the courses, that is DA and CS. So let us solve the first question on CS. Okay. So before I begin, just one small thing, and then once again, let's look at a quick glance over the syllabus, what we have covered, what we have not. Parts grayed out are the parts that we have covered. In essence, supervised learning, heuristic regression, KNN, naive Bayes, cross-validation like LOO, K-folds, cross-validation, multi-layer perceptron. Multi-layer perceptron we have not covered yet, but we have covered perceptron. We'll cover that in feed-forward neural networks. So that I wanted to say I covered perceptron. Today we'll be covering linear regression, multiple linear regression, with regression, and bias variance trade-off. Four topics might seem a bit daunting, but no, it's not. The first three topics are very related to each other, while bias variance trade-off is the other topic that we will study. We'll spend an hour on that, another 40-45 minutes on the bias variance trade-off, and that will be the class. Okay, fine. So this is the question on DSA. Maybe I'll give you guys about 2 minutes to solve, and let me know the answer. Okay. Any answers? Yeah, very simple. So for a queue, you can perform and so for a queue, you can perform both NQ and DQ operations in order of one time. We'll also discuss some practice questions about what we learned till date. Okay, some could be new as well. That will also help you to learn some new things. And whatever we learned till now, whatever we are learning now, which is machine learning. Um, Machine learning, when you want to apply the method to a large data set, then that is called a data mining. Next question is a question on KNN. Read this and try to answer. Yeah. So what is the KNN algorithm? The KNN algorithm is non-parametric algorithm and does not make assumptions about the underlying distributions or data. So what is a non-parametric algorithm? If you remember perceptron, we were trying to find two values, W and B. Similarly, for logistic regression, we were trying to find the values of W and B using MLE that best estimates the data set. When it comes to KNN, KNN has no parameters, right? You just look at the data, you plot the distribution, then try out different. When we have a test data set, you look at the closest k data points, and then you predict the output based on the labels of these neighbors. Okay? That is the point B actually. So A and B both are correct. KNN algorithm, lazy machine learning algorithm, it can work well. Yes, anything that works for binary can also work for multiple class classification problems, because if you remember, there is something called one versus all, which we discussed in the last class, which you can convert any multi-class class classification problem into a binary classification problem. So that is why option D is the correct answer. Next is, how will you handle imbalanced data in a KNN dataset? So what do you mean by imbalanced data? Imbalanced data would mean, let's say that you have a cancer dataset. So your dataset, the people who do not have cancer, let's say, are this. Okay? And someone who has cancer, let's say his data point, you plot as here. Okay? And maybe also here. Okay. Now, if I have a test data point, let's say this is the test data point, and my value of k is 5. Okay. What will the model predict? It's very simple. It will predict that it does not have cancer. He or she does not have cancer. Even if I place it anywhere here also, then also I will get the same, right? Because the majority is a no cancer. So this can hamper your prediction. The value of this cancer cell is not too much. So what you can do is, there is something called sampling. So you modeled the data set as a problem P of x given. Given the cancer class y equal to cancer, using this probability distribution, you can sample more data from it. Okay. And by sampling more data, you're trying to oversample the class that is minor. Minority class. So there's a term called minority class here. What minority class means, the class which has lesser data points. The class which has less data points in the cancer data set is the person who has cancer, right? Let's say this is the X, this is the cancer data set, where your Y is either the person has cancer or person has no cancer, right? In this case, the class cancer has lesser data points. So what you can do is, you can model the probability distribution Px given y using any method. You can use naive Bayes also, that's fine, because naive Bayes actually does this only. It tries to model it as a probability distribution. Given the y as cancer, P of xy denote the probability, and then you can sample more data points from this distribution that will form your, then you will get more data points, and that will oversample the minority class. So B is correct. The other option you can do is you can see the minority class, majority class, which is the person who do not have cancer, and you try to remove some data points from it in order to balance it out. That is not a very good option to do because you're cutting down your data set. It might hamper your accuracy. It might, because it's not always it will hamper. It depends on the data, but that's not good to always remove data from your data set. So see, but you can do that to balance it. And the option A is weighted voting. So what do I mean by weighted voting is when I have this point, if I see a cancer data point, I won't count this as 1. I will count this as some other value. I will give it a weight of let's say 0.7 and others as 0.3. And then if something is greater than the threshold, then I can say that the person has cancer. So in that way, what I'm doing is I'm trying to value the minor class a bit more, because a person who has cancer has more, is a more of a threat than a person who does not have cancer, right? So weighted voting, where the vote of each neighbor is weighted by its inverse distance to the query point, is just given one example heuristic of how you would want to weight it. You can use any method, but weighting is also an option to handle imbalanced data. So all three are options. Option D is the correct answer. Okay. So let's begin talking about linear regression. Okay. Linear regression, as we all know, is a regression where your um, prediction variable, which is your y, belongs to a real number. So in a sense, it is continuous. Okay, and so what we can say from our previous lecture, the probability distribution of y given x, we can start with something like, given the point x, what is the likelihood that you will observe that y is nothing but 1 by 1 plus e to the power minus w transpose xy. Okay, this is what we saw in the earlier lecture. How we can look at the earlier lecture, I have already full derived this thing. Okay, and we also looked at the loss function corresponding to this probability distribution. It's nothing but sum over I equal to 1 to n log of 1 plus e to the power minus w transpose psi 1. Again, this is done using MLE. You can look at the previous lecture where I have talked about it very extensively. Now, if you look very carefully, let's take a data point where it can be of two cases. Okay, just a minute. Okay. So data point can be of two cases. Case 1 is that it is classified correctly. Okay. So I'm just still talking about uh, classification, but just hold on. Is correctly. Let's say I've classified it correctly. Then how do you think for this given data set, for this given loss function, how would it change? In a sense, let's say this is classified correctly, which means the product of W transpose Xi and Yi is positive, right? If Yi is negative, W transpose Xi is also negative. If Yi is positive, W transpose Xi is also positive. Now, what you are doing is you are taking a log of e to the power that. You are taking an exponential power of that value. It could be 1000, it could be 2000, any value it could be. And there is a minus sign. So e to the power minus 1000, e to the power minus 2000. So so if you know, your loss will tend towards 0, because your dominant term in this scenario will be this exponential term. It will dominate so much, and e to the power minus infinity is what? 0. And log of 1 plus 0, log of 1 is 0. So that's why if you're correctly classify the data point, then your loss tends to 0. The case 2 could be incorrect or wrong classification. So your loss, given that scenario, will tend to what? Can you think for a minute? Okay. So think now. If your classification is incorrect, then your yi is positive, w transpose xi is negative, or w transpose xi is positive, yi is negative, and so your it is e to the power some positive term. It could be another positive term, and e to the power infinity is what? It is infinity, correct? So your dominant term in this scenario, your dominant term in this scenario will be whatever is present in, and yeah, okay. So e to the power positive term and log of e to the power positive term is what? Is the term itself, right? Log e to the power a is a itself. So your dominant term in this scenario will become minus w transpose xi by n. Okay, okay. So with this knowledge, let's go ahead. Again, why I told you this, you'll get to know in just a second. Okay. So now let's start with linear regression. In a linear regression model, what you do is, let's first state the assumption. The assumption is very simple. If you have a set of data points, okay, okay, let's say these are some set of data points you have, you can fit a line linear equation through those data points, correct? So that is my first assumption. First assumption is the equation of y can be expressed as linear. And the second assumption that we make is, for each value of xi, there exists a Gaussian distribution. Again, why I will explain, just let me write the statement. Gaussian distribution that models the true value of xi. I will call it psi I or sigma I. Okay. So what I'm trying to say here is, if you, let's say, look at this line, look at this point, right? So this is nothing but your W transpose xi, correct? And you are now off by this psi I. So what I'm trying to say again is, another way you can look at it is, there could be some scenarios where your one single data point xi maps to multiple yis. For example, let's say that let's take a house. Okay, you have some set of features for a house that models your xi, and those the same. There could be another house with the same set of features, but the ii could be different, right? So what we can say is the Chi I, which is sorry, the sigma I, which is your sorry, the epsilon I. Okay, the name of the thing, epsilon I, which is the difference between the true value and the true value. We can express it as your yi. Just a minute, guys. This pen is having an issue. Okay, fine. So your yi is nothing but W transpose xi, which is your prediction that you are making for that line, for that point xi. What does the line say? Plus y. Oh, sorry. Come on. Okay. Plus epsilon I. Okay. So your point was here. Your line predicted here, which is W transpose xi. And your epsilon I is the difference between the true value and the incorrect value. So your epsilon I, as I said, is modeled as a Gaussian distribution having some mean, in this case 0, and some variance sigma square. And if you know Gaussian distribution, our W transpose xi, as I said, our individual y's can also be different depending on the xi's. So our yi is also distributed around W transpose xi as a mean and sigma square. I hope you understood this. This is also one of the, as I said, prerequisite of what happens if you add two normal distributions, what happens to the mean. Right? So in essence, what I can say is probability of seeing that yi given xi and w is modeled as a Gaussian distribution with this PDF 1 by sigma, 1 over 2 pi sigma squared e to the power minus 1 by 2. Now my x here is yi, right? So, and my mu is W transpose xi by sigma whole square, correct? Now, this is the probability of seeing the yi given the xi and w. Now, the main question here, the main thing that question here is, how do you find w? Because if you find w, then that is enough, right? You have solved the question, right? Now, think. Um, So one thing that you might be wondering now is, where did the B go, right? Is this always passing through the origin? Not always. Okay, it might not also pass through the origin. But if you remember, I have implicitly used that trick from now, what we used in perceptron, which is just add a new dimension, incorporate the B to the W, and add a new dimension with all ones in X. So now the question boils down to is, how do you find the W? Now there are two ways to find W. Okay, one way is to use something called maximum likelihood estimation, abbreviated MLE. So first let us look at this derivation, and then we'll look at an alternate way as well, and what do you get by doing that as well. So maximum likelihood expectation estimation says that your W star, which is your optimal W, is nothing but argmax across all W, the product across each data point I equal to 1 to n, probability of seeing that yi given that xi and w. Okay. Now what I can do is I can take something called the log if you see a product. So argmax w sigma I equal to 1 to n log of p of yi given xi. So this is just the basic log property. Product becomes a summation. And now I can substitute the value of the normal distribution here. So argmax of w summation I equal to 1 to n log of 1 by root over 2 pi sigma square e to the power minus 1 by 2 w transpose xi minus yi by sigma. So you might be wondering, why did I interchange w transpose xi and yi? Think again, okay? It's the same thing that if you write it anyway because it's square. Okay. After this, what I can do is I can separate the constant out. Log AB is log A plus log B. Argmax of W I equal to 1 to n log of 1 by root over 2 pi sigma squared plus now log of e to the power something is nothing but that something, so minus 1 by 2 sigma squared w transpose xi minus yi squared. Okay. Now if I ask you to find the value for w for which this function is maximum, if you look carefully, the first term, which is this term over here, right? This term over here is a constant, right? And you differentiate a constant with respect to w or any x, what you get is 0. So I can assume this is 0. And not consider this term because if you want to find out it, then there's no point in it. Okay. Now what I can do here is, now this becomes argmax of w I equal to 1 to n minus 1 by 2 sigma squared w transpose xi minus yi squared. And the other thing that I can do here is, this is the maximum, so it's a minus negative. What I can do is I can negate it to find the minimum. So this becomes argmin given w summation. Another thing that I can do here is this, since we are trying to find the value for w for which this function is the minimum now, we can ignore the constant as well, 1 by 2 sigma squared, and write this as summation I equal to 1 to n w transpose xi exceeding the limit. Maybe I'll remove this word. W transpose xi minus yi. Okay. I just ignored the constant 1 by 2 sigma squared, and I also negated the minus, so that now it's a minimization problem. And This looks okay now. So what you can do is you can try to minimize this, you will get the right answer. But for explainability, which is if you want to explain your loss to some person, if you want to explain the loss of the model to some person, the better way to do is to use something called the mean squared error or average of it. So what you can do is, instead of this, you can write the optimal W is nothing but the average of uh, argmin of W 1 by n summation of I equal to 1 to n W transpose xi minus yi. So this equation is very important for linear regression. This is the function that you have to minimize and find the W that will give you the best fit for your given data. Now, how do you, now the thing is, how will you minimize this? If you saw the last class, we used a method called gradient descent. And let me give you the good news here. Since this is a quadratic function, this function is convex, which means the loss will look something like this. So you are always guaranteed to get the global minima. So you can use gradient descent to uh, find out the optimal W. So this was one way to find out what is the optimal set of parameters to arrive at the solution. The other thing that you can do is there is another method that is called maximum a posteriori maximum a posteriori or map. What map does is, if you want to find out the probability of W given a data set, which is, let me write this as D, where D denotes your data set, probability of a given W given the data set D, okay, where your data set is nothing but set of xi yi's. So your data set is nothing but set of xi yi's. Okay, is nothing but just applying the Bayes rule here, PW divided by P of data. Okay. And just like naive Bayes assumption we had, we will ignore P of D because that is not changing across different W or different yi's. So we'll ignore P of D. Okay. We won't calculate P of D because that doesn't make any sense to calculate it. What we can do here extra compared to what we were trying to do in MLE was we can have a prior belief for W. Okay, which means we can assume PW, which is a prior, before looking at data set. What do you think is the distribution of uh, the weight W? Is nothing but, let's say it comes from a normal distribution with mu 0 and tau as the standard deviation. This is my prior belief of PW, and which means my P of W is nothing but 1 by root over 2 pi tau square e to the power minus 1 by 2 x. So mu is 0 here, and w is a vector, so it becomes w square is nothing but w transpose w by tau square. If w is a vector, then w square is w transpose w. So now the things become very similar. See, p of w, what is the probability of the weight w given your data set is nothing but probability of the data given the w multiplied by the probability of w. And here, maximum a posteriori estimation, what it does is, it also assumes the same thing, which is your each xi yi's in the data set are drawn independently. So what I can do is, I can take the product of each data point, in the sense, I will try to find the argmax which w is present, such that the product across each data point yi given xi comma w is maximum, multiplied by the probability of multiplied by the prior probability. And as always, since it's a maximization problem, or it's a problem where it contains products, we can use log to convert it into summation. This goes very similar to what we saw some time back. Log of p of yi given xi comma w multiplied by p of w. Okay, I'm just taking the log, nothing else. And this one, again from the previous lecture, this is nothing but not previous lecture, 5 minutes back, argmin of yw summation of I equal to 1 to n 1 by 2 sigma squared w transpose xi minus yi whole square plus, now what I'm trying to do is log of pw, also I'm trying to estimate the maximum, and if you calculate for this one, you will get something like this, very similar to the previous one. And now I can write this as argmin across w. We can take the average summation I equal to 1 to n w transpose xi minus yi whole square plus lambda and the L2 norm of W. W transpose W is nothing but L2 norm squared of W. L2 norm is nothing but root over W transpose W. If you do the square of it, you get W transpose W, where your lambda is called sigma squared by n into tau. So if you substitute the value of lambda here, you will get back the equation on the top. So this equation here, you see this extra term which comes from your prior belief. This extra term. This one remains unchanged compared to what we had earlier. This was the extra term, and this is called ridge regression. And what is ridge regression? Whenever you are trying to estimate the optimal W for a given set of data set, for a given data set, you have some prior belief, which is your PW comes from a normal distribution. Using that prior belief, you try to model the loss function, and the extra factor that comes is called regression. Is called ridge regression, and the lambda over here is called your regularization factor. Okay. Again, if you did not understand this, maybe look at the recording again. It won't be very difficult. Okay, but I assume you have some experience with the previous lecture. You have watched it. Okay, so this was ridge regression, and now simple, now it's done actually. So simple linear regression is nothing but, so given a set of data points, let's say xi, if you have only one feature, which is each data point contains only one feature, then that is called a simple linear regression. And if you have multiple features, so in notation, I can write this as number of features d is 1 and multiple linear regression, the set of features is more than 1, which is your d is greater than 1. So that is the only difference between simple and multiple. Rest everything, all the derivations and all remain the same. Okay. So this was all I had to talk about linear regression. And what we will do now is we will talk about one of the most important topics of this entire course. Okay. And I can't stress upon what is how important it is, which is called bias variance trade-off. So this is a totally new topic we will discuss now, and this does not require any knowledge on machine learning only, to be honest. This is more of a probability lecture today, rather than, but not much of probability, only that you should know the formula of the expectation. And but this is a very important topic, and you will learn many things from this today. Okay, so let's start. So you are given a data set. Okay, you start machine learning given a data set of some points x1, y1, x2, y2 till xn, yn. You have n data points. And let's take a regression problem, which is each yi belongs to the set of real numbers. Now, as I said, let's take example of house prices. Given a set of features x, given a set of features x for that house, the same set of features, let's say your features are, let's take an example. So your features are square feet, how much square feet the house is, number of rooms, location. Let's see, okay? Okay. And your y denotes the price of that house. It could happen that, let's say I have a data point which is like 1000 square feet house, 3 bedrooms, location is, let's say, Bangalore, and the price is, let's say, 1 CR. Okay. It could also happen that you saw some other house which is also 1000 square feet, which also has 3 bedrooms, which is also in Bangalore, and its price is also one. Its price is, let's say, 2 CR. One could be a house that is maybe in a posh locality of Bangalore. One could be it is not in a posh locality of Bangalore. You can imagine anything. So it's in Bangalore. They are saying you just have that feature. You don't have the feature of which area is it in Bangalore. But depending on the same set of features, you can have different vibe, right? So that is the point that I wanted to say here. So your probability that of observing x and y is nothing but the probability that given that x, what is the probability that you will observe that price multiplied by what is the probability of occurrence of that x. Now, Let's say you have infinite data points, infinite set of data where you collect all the price of all the houses in Bangalore. And what you do is for a given data point, so for a given data point, which is X, you would want to find the expected value of that house. Okay, let me say again. Like this, let's say you collected about million data points, all having the same feature. 1,000 square feet, 3 rooms, Bangalore, all having the same feature, and all of them have their corresponding y's. So what you can do in this scenario is you can calculate the expected value of y, which is y bar of x. Okay, so y bar of x is nothing but the expectation of y given that x is equal to the summation across the integral across all y's, because y integral, because yi is continuous, it's a yi belongs to a set of real numbers, and if you remember the formula of expectation, then you will have to take the integral across all y's, the value of y multiplied by the probability of observing that y given that x dy. Okay? Let me explain it again. This is very important. So what I'm saying here is, it could happen that, let me put this here, it could happen that given a set of features, let's say the features for a house in this scenario, all the values are the same, which means if let's say you are collecting three features, one is the square number of square feet of the house, number of rooms you have in the house, and the location of the house, and your y denotes the price of that house. It could happen that let's say you have 1 million data points and all of them have the same value. All of them have 1,000 square feet, 3 bedroom, and all are in Bangalore, and all of them have their own set of prices. Let's say this is 10 CM. Okay, all of them have their set of prices, which means we can model that for a given x, the probability of observing that y can be thought of as a probabilistic distribution, where this is nothing but the total law of probability. So p of x and y is nothing but p of y given x multiplied by p of x, which is the law of total probability. So p of x comma y is, what is the probability that given that set of features x, you observe that y multiplied by what is the probability of that feature vector coming in the first place. And since we modeled it as a probabilistic probability problem, probability distribution, then what we can do is we can estimate the expected value of that house, which is across all x's, across all a given x. What is the expected value of y? Which is nothing but the expectation of y given that x is given, which is nothing but the integral across all output house prices you have for that given x. Again, we are in the conditional space. For a given x, y multiplied by what is the probability of occurrence of y given the x dy. Now, another thing that we will consider here is, so this is also called, so y bar of x is also called your expected label. So y is nothing but your label. So y bar of x is called the, what is the expected label given that data point x. Now, let us say that h of d, which is the hypothesis for a given data set, denotes the hypothesis of using any machine learning algorithm A on that data set D. So if you take any machine learning algorithm that you have learned till now, it could be KNN, regressor, could be linear regression, it could be any algorithm that you learned till now, which is A. I'm abstracting that out. If you apply that on the data set D, HD denotes the hypothesis that you get by applying that algorithm on the data set D. Okay. So, given this information, what you can do is, if you are testing this model, so what is your expected test error? Okay. Just let me write this down, then I will explain. Expected test error, given your hypothesis, given a particular HD, is nothing but your expectation that your XY you sample from D, sorry, your X comma Y is a data point that belongs to D as data set in this scenario. What is the output given by your model, which is HD of X, and how off are you with the true label, which is Y? So, given a test data point, which is X comma Y, you input X to your machine learning model, which gives you a Y. Let's call it Y dash, which is your model's prediction of Y. Y dash minus Y denotes the error, how far you are from the true value. And if you take the square, then you try to balance out, then you try to also take care of the negatives. Okay. Okay. Given a set of data points, X comma Y, but if you remember, I told you, when you are looking at the test data set, you are not allowed to, you may not be able to see the Y at all, because it could be a new data point that you are trying to predict. You don't know the true level. But again, we are talking in theoretical terms today. So that is why this is absolutely okay. Okay, just a minute. Okay, please give me a minute. Yeah. So as I was saying, I had a power cut. Sorry about that. So as I was saying, the expected test error given a particular hypothesis H of D is nothing but what is the expectation that across each data point you see X comma Y belonging to D, your model's prediction, which is HD of X minus Y whole square, how off are you from the true value? So I can write this as integral over all X, integral over all Y, HD of X minus Y whole square dy dx. This is just extending from the formula we found for the classification, for the expectation. Okay. Fine. Now, now let's think of this point very carefully. What I'm trying to say here. You had your set of data points, right? You had your set of data points, which is xi, yi. So each data set x comma y, you sampled it from some probability distribution. Let's call it PD. Okay, you took some probability distribution PD, and you sampled the data points x comma y. If you somehow knew what is the PD, what is the distribution probability distribution PD, then you don't even have to learn machine learning because you know the probability distribution you can estimate for any x. But we don't know that, and that's what we do. We try to estimate this distribution. So that means what I can say is each of these xi, yi's are your random variables. And since you apply an algorithm A of D on those random variables, H of D is also a random variable. So what I can say is the expected classifier. Okay, let me uh, first write and then I will explain. Let's call it H dash of X is nothing but expectation across a data set drawn from the distribution P, the summation across all data sets HD P D D D. So what do I mean by this is you sample n data points, which is Pn, and you sample infinite set of data, infinite set of training data sets, which is your Ds, and you sum across every D what is the value of that particular HD multiplied by what is the probability of occurrence of D, PD, given that data set D. So again, let me repeat. P of n denotes you're trying to sample n data points for the probability distribution P, which is D drawn from Pn. AD denotes your algorithm that you apply on the dataset, which also means that summation across all datasets you draw D, what is the value of that algorithm AD multiplied by the probability of occurrence of the dataset D, DD, and that will be your expectation. So now the thing that we want to actually calculate is the generalization error. What do I mean by that is what is the expected error of your model, which is your A, your algorithm, is nothing but expectation. You draw the test data points x comma y from a probability distribution P. You draw your data set, which is n data points from again P. So D denotes your training data set, and x comma y denotes your test point. What is the expectation of HD of x minus y, which is a generalization error, which means after you have sampled n data points from P and made it D, the hypothesis that you made by applying the by applying A on the dataset D, if you apply that hypothesis on a test point X, how off are you with the true label Y? And this is what we want to estimate, right? You train your dataset, you train your model using a set of data points that is D, and how does it perform? What is the general error? What is the expected error given us test data point x comma y drawn from P? So what I can say here is this is nothing but the summation across all D, the summation across all data points x, the summation across all data points y. What is the expectation HD of x minus y whole square P of x comma y P of d dy dx dd. This is just the formula of expectation. I hope you all know this. If you don't, then please revise that. That will be better. Then what I can do here is I will apply one trick here. So what I will do is, so I won't take this formula. I will take the earlier one, which is this one, and I will add and subtract h dash of x from both sides, which what I mean is the expectation. Okay, let me write it fully so that you understand. Given a test point drawn from P, given a data set D, which is a set of n points drawn from P, hd of x, which is the value from my hypothesis, from my model, minus h dash of x plus h dash of x minus y whole square. So if you look carefully, I have done nothing here, right? What I have done is I have just subtracted h prime of x in this equation and added h prime of x, and that I have put them in bracket. Okay. Right. So now what I will do is I will expand this term x comma y belongs to P, D belongs to P to the power n. So let me write this only as expectation. Let's not clutter it. It's the same thing. Okay. So what I mean is expectation of hd of x minus h prime of x whole square plus expectation of h prime of x minus y whole square plus 2 into expectation of hd of x minus h prime of x minus y. Okay, this is just if you apply the formula a plus b whole square on an expectation data set, on an expectation, so you get this one. So expectation, so let me write down the formula here. Expectation of a plus b whole square is nothing but expectation of a square plus expectation of b square plus 2 into expectation of ab. So this is something similar. So expectation of hd of x minus h bar of x whole square plus and so on. Okay. Now what we will do is we will look at each of these terms one by one. Okay. Focus on the term first. So let's focus on the easy part. Okay. The easy part is if I tell you now that your life will be simpler if I say that the third term actually evaluates to 0. This is not because I said, there is a proof I will do. If I say this term is 0, the third term, then we can only focus on the first two terms, right? Okay. So I claim that this third term, which let's say I call this third term, is evaluates to 0. So what is the proof? How can I say it's actually 0? The third term says, let's ignore the 2 because expectation doesn't matter. So expectation of x comma y comma d, h of dx minus h bar of x, h bar of x minus y. Okay. Now if I just put the expectation inside here, now, so what I mean is expectation of xy. What is the expectation of d given hd of x? We just looked at it. So across a set of data points. What is the expect data set? Sorry. So, okay, let me first write. So, what I'm saying is across a set of data sets D, the expected value of HD of X is nothing but your H prime of X, which is your expected classifier, correct? So, if you have a classifier HD of X, if you sample infinite number of data points, data sets D, and try to find the expected classifier, that is nothing but H prime of X. So, this is H prime of X, and this is H prime of X. H prime of X minus H prime of X becomes 0. So that's why this term here evaluates to 0. Okay, fine. I'm not writing it down because anyway I'm lost annotations. Fine. Okay. So this term is gone. Okay. I hope you are with me. Now let's look at the first term. Okay. First term is simple. First term is the expectation across x comma y comma d, the value that you predict from the model HD of x minus the value that would have come from the expected classifier, right? Which also means you had your model HD of x, H prime of x denotes your expected classifier model across each data sets. How vary are you? How different are you? What is the variance between the model that you have, which is HD of x, against that of the expected classifier H prime of x. And this term is nothing but your variance. Now, if I ask you a very basic question, should your variance be less or more? The answer is obviously it should be as less as possible. Why? Because if your classifier H of D or your model H of D, let's not have a classifier, any model H of D hypothesis, it should be as close as possible to the expected classifier or expected model, which is H prime of X. Then you have actually built a very good model because your model is able to generalize very well across all data sets. Okay, so your variance should be low. Or in other words, how different is your model from the best or the expected classifier? This was your first term. The second term, which is expectation of x comma y comma d, h prime of x minus y. So again, let me just, so we looked at this term. The first term we looked at h of dx minus h prime of x whole square. We are now looking at the second term, h prime of x minus y the whole square. And what I will do here is, I will apply the same thing I applied earlier. So what I will do is, I will add and subtract y bar of x. Okay. So what do I mean by it is, okay, what do I do is expectation x comma y comma d h bar of x minus y bar of x the whole square, right? Plus okay, so what I'm trying to do is, okay, let me first write it out. So this is my first term plus y bar of x minus y of x the whole square. Same. Previously we were doing h prime of x minus plus minus of h prime of x plus h prime of x. Here we are doing minus y prime of x plus y prime of x. So what I can do is I can expand this out again. So expectation h prime of x minus y prime of x whole square. Okay. Whole square plus expectation y prime of x minus y of x whole square, right? Plus 2 of expectation h prime of x minus y prime of x multiplied by y prime of x minus y of x. Okay. Okay. Now again we have three terms, but there is another good news. The third term will always evaluate to 0. Why? So expectation of x comma y comma d, expectation of y across all y of x. Okay, so what you are now doing is instead of a single y of x, which is your test data point, the true label for the test data point x, you will try to find out across all x's or across all x comma y's what is your expected value of y, and that is nothing but again y bar of x itself. So that is why your third term will be 0. And now focus on the first two terms. The first term here, this gentleman says, okay, your model, the expected model is h prime of x, and your expected y is y prime of x. The expected model or the best classifier you have is h prime of x, and your expected y across all different x data points is y prime of x. What it could happen is, let's say you are considering all possible set of linear equations, okay, and you try to estimate it using h prime of x. But it turns out that the model you are trying to fit is actually a polynomial regression problem. So your model has a bias. The bias is the model is biased towards linear relationship, and so the expected value of your test data point x, which is y prime of x, how off are you from your expectation, from your expected classifier, which is h prime of x, is called your bias. Again, let us say that you have a data set, and for some reason or the other, you try to fit a linear regression model. These are the different models you predicted, each of them different models. Now, across each data set D, if you take the expected classifier, expected model, you get h prime of x. And given those set of data points x, you have an expected test label, which is y prime of x. Now, let's say your data set was indeed not a linear equation, it was a polynomial fit. So your correct model would have been a polynomial instead of a linear. But your assumption was it could fit in a linear equation. So considering your assumption that you are assuming a linear relationship, how off are you compared to the expected value of y is your bias. And this term here, second term, is nothing but your expected value of y that you calculated. How off are you as compared to the true value of y? So your expectation of y was, let's say, 5. The true value of y is 4. It's a new data point, and it's a new data point. Let's say you are looking at all the houses and your expected value of house given this set of features x is 1 CR, and there is a new data point x comma y. X is the same as the earlier x's you have, only that your y, which is a true label, is the price of the house that you are now looking at, is 1.2 CR. So 20 lakhs is your error here. So that is why, so y dash of x denotes the expected value of y given the data set you saw, and yx is actually the true label of the test data point. How off are you? And this is called the noise. Okay. So with this, a very, very, very important conclusion from today's lecture, which is the generalization error of any model that you are trying to build right is nothing but the expected value of what your model has predicted minus the expected classifier, which is your variance. Okay. Plus what is your expected classifier minus your expected value of y, which is your bias of the model. Okay. Plus your expectation of the expected value of y from the true level of y, which is your noise. Okay. So so if you plot this as a graph, so let's say, okay, let me draw it properly. Okay. So here it denotes your model complexity, which is with time you train your model, you add more features, you try to improve your model with time, right? Model complexity, and on the y-axis denotes your error, which is a generalization or your error. Okay. As the complexity of the model increases, so let your bias and variance tend to follow this relationship. So where your bias is high, your variance will be low, and when your variance is high, your bias will be low. So this is called the bias variance trade-off, and this denotes your total error. This denotes your variance, and this denotes your bias. And the best model will be somewhere that balances the bias and variance trade-off. So let me go again. Your bias and variance tend to follow a inversely proportional relationship, which means if you have more bias, variance will be low. If you have more variance, then your bias will be low. And it could also happen that you are somewhere, let's say, here, right, where your bias and variance are both high, we can say, or you are here where, so you can have all four scenarios as well. So let me explain. So to explain this, I will draw a simple diagram. The X denotes your bias and the Y denotes your variance. Your variance could be low, your variance could be high. Your bias could be low, your bias could be high. So, okay. So when your variance of the model is low, so let's take this as a dart game. So this is your dart game, and you are trying to shoot darts. Let's say your model is trying to shoot darts. And how will the model behave if it has more bias or less bias, more variance or less variance? So if your model, yeah, fine. So if your model has low variance, which means you are not very off from the expected classifier, and also your bias is low, which means whatever you expected from the model, whatever was the expected value of the expected classifier, is almost same as the expectation you had from the data, then you're always trying to hit the target very, then you're always trying to hit the target. So your variance is low. See, all the targets are hitting, they are not very spread out. The spread of the targets are very pinpoint. Okay. But when your bias is low and your variance is high, which means your average value across all x's might belong to the correct value, which is the center, but your variance is high, so you're trying to hit more across the boundaries as well. But all in all, the average across all this is the average across all this is low. That's why your bias is low. When your bias is high and your variance is low, then you are off from the target, which is your model is not able to properly model the data set. But whatever you are hitting, even though it's off from the center, off from the optimal value, it is still less spread out. And in the last case scenario, not sure why it zooms in always, but okay. And in the last case scenario, when your bias is high, so you are hitting any randomly anywhere, and your variance is also high that you don't know where you are hitting, then maybe you are drunk. Okay. So typically machine learning models don't fall into this scenario, which is having a high bias as well as high variance, because that is a very, very poor model. Or and low bias and low variance is a perfect model that can have chances of overfitting. Again, what is overfitting and different? I think I've taught about it, but still I will go through it again once in the near future also. So typically what you have to know is in this topic, this graph, bias variance trade-off, more the bias is the variance, more the variance is the bias. Your generalization error, how do you compute it and how it has been decomposed into different components? What is your variance? What is your bias? What is your noise? And bias variance trade-off actually helps you to build a very perfect model, in the sense now you have lot of more info about how your model is performing compared to the gold standard, right? And across each configuration of variance and bias, how does your model behave? Okay. Okay. So what I will do is I will stop here for today. Okay. We have learned a lot of stuff today. Uh, so with today we have covered simple linear regression, multiple linear regression, regression. We have covered bias variance trade-off. In the next class, I will talk about linear discriminant analysis and something called PCA because they are related. Dimensionality reduction. So dimensionality reduction means if you have a set of data points having D features, right? Having a lot of features, and let's say you don't have that much compute power to actually use those D features, or you want to shorten, you want to eliminate some features, you can't just blindly eliminate any feature because some feature could be more important than the others. So how efficiently or how can you um, reduce the dimensionality of your data, keeping in mind that you don't miss out on the important features? And there are two ways to do it. One is LDA, linear discriminant analysis, and another is the principal component analysis, PCA. So in the next class on Saturday, which is a totally new topic, we'll discuss these three topics. On Sunday, we will discuss support vector machines and decision tree. I doubt I will be able to complete support vector machine in 1 hour, but I will still try my best. If I complete, then we'll look at decision trees, and then that will only leave you with feed-forward neural network and clustering algorithms. And I think that should be the end of the syllabus. So I believe we can finish it by next week for sure. If I have 3 classes next week minimum, then we will be able to finish machine learning overview. Again, I'm not going very deep into machine learning now. There are much more intricacies. I could have solved many more numericals on each topic as well, but time is not that much with us. You also have to revise, you have to study this also. So that's why I'm not teaching you in very depth, but still I'm trying to at least clear some concepts that will help you in the exam. Okay. Uh, okay. So what I will do is